Okay. So I will give you a warning. This is probably what you would call bad teaching, but I'll give you a warning. This is a hard lesson. Okay. So you best be on your mental game. Friday afternoon before Labor Day weekend, huh? Sure, you're out your best. We'll see. Maybe I'll teach it so well that it'll be a miscanner-related rates kind of thing. Well, we'll see. Okay. You'll find the homework is pretty light, but the notes are pretty heavy. We'll go through most of this together. All right, so the notes are blue. Here we go. The idea is estimating area under a curve. Note it says using rectangles, not using fundamental theorem of calculus. So, using rectangles, here we go. Could you estimate for me the area under that curve using left, right, or midpoint rectangles of equal subdivisions? For example, the area under x squared plus 1. La-di-da-di-da. Let me show you how much I would like to see. If there are equal subdivisions, let's go left hand here first. Did I say left hand first? Yes. Okay. If there are equal subdivisions, then doesn't each rectangle have a similar component?
Yeah.
What is it? If they're equal subdivisions from 0 to 8, using
equal width.
They're equal width. So either width or base. I'm going to factor out a general base. And then as far as the shape of the curve, we'll have 4 heights for each of the rectangles. This factored out base is only if they are equal bases. Obviously, if the bases are not equal, which will happen a lot in AP problems, then that's not done. In this case, what is the base? 2. How'd you get that?
8 divided by 4 equals 2.
Yeah, 8 minus 0 for the total region divided by 4 into 4 chunks gives you each chunk is 2. Yes? Surely, when I'm not doing this in notes, I would probably just go to 2 just like you did. It is important to me that you communicate where you pull your heights from. So this step is important. Height 1 is the function at what value? Using left-hand rectangle.
0.
0. Okay, so the first height is f at 0. The next is f at 2, 4, and 6. Okay. That part is usually graded pretty hard for on the AP test. You must communicate where you're getting your values. Don't just give me values. F at 0, 1, F at 2, F at 4, and F at 6. Mentally, what is 1 plus 5 plus 17 plus 37? Yes, mentally. By the time you said mentally, you could have done it. 60, 70. This is so sad.
120 is the answer.
It is 60. And that's 120. All right. The midpoint method, right hand is next. Let's go straight to, it's still going to be the same first step, so let's go to the second step of 2 times and start where we're going to be different, which is the heights. F at
2.
2. Now we're using the right hand of every region. F at 2 plus
4
plus
6
plus.
Okay.
Okay. What is F at 2? 5 plus
37
plus something new. 65. Again, mental math. 102, 19,
4 20.
37, which is 14, that's 54,
124. Okay, for the midpoint, F at. Okay, now each subinterval, the subinterval is 0 to 2, so the midpoint then is 1, F at 1. Then,
F at 3.
then,
F at 5.
then,
F at 6.
okay, all these are new. What is F at 1?
2.
F at 3, 10, 5, 9, sorry, 10, 26, and 50. Sum 76, 86, 88.
Yeah.
And product 176. Okay. Which do you reckon is the most accurate?
The midpoint.
The midpoint is the most accurate, typically, of the three. We will eventually get on to right-hand only, but we'll build up to it. Next, it's besides equal subdivisions, you sometimes want to use unequal subdivisions. For example, if you're working without a calculator and you don't know the square root of 2 and 6 and so on, you might break it into unequal subdivisions. So, say we had the square root function on 0 to 16 and 4 left-hand rectangles. Again, actually, not again. So, can I factor out a base?
Nope.
I cannot. I'm going to break this curve up into different lengths. If you're visual, I actually, if I were in your shoes, I'd probably be drawing this because I am visual, but I've done this so many times I'm not. 0 to 16 is not going to be broken up into equal subdivisions because I don't know the square root of 8 nor 12 very well. So it would be logical to break it up into 1, 4, and 9. Okay? That said, we cannot factor out a common base, so it's more like base 1, height 1, plus base 2, height 2, plus base 3, height 3, plus base 4, height 4. Base 1 is 1, coming from 1 minus 0. Height 1, using left-hand rectangle. F of, what's the left hand? F of 0. Okay. The next base is from 1 to 4. I'm going to write 4 minus 1 just to communicate where that base is coming from, although they aren't very picky that you show that part. If you went straight to 3, that would be okay, but I would like my notes to communicate where that's coming from. What's the second height using left hand? That region is from 1 to 4. Once you start to know where to look, it's really easy. It's from 1 to 4, so what's the left-hand region? F of 1. Okay. The next base is from 4 to 9, so it'll be 5 wide, and F at 4, and the last base is from 9 to 16, and we'll use F at 9. Cleaning this up, I'm talking 1 times 0 plus 3 times 1 plus, you'll see a pattern emerging, 5 times 2 plus 7 times 3. First number is an odd pattern, second number is just an ascending whole number pattern. So 0 plus 3 plus 10 plus 21 is 34. Okay. Right hand. Would you try right hand? You do not have to show me that first step, nor do you need to show the calculation behind the bases. I do need, however, to see the F at part. What'd you get? I got 50. How about you? If you got 50, great, move on to midpoint. If you didn't, oh, there's no midpoint, sorry. There's no midpoint. Don't want to do midpoint. That said, it was, again, we're talking no calculator days, it was to the kind of simple person, they would say, well, I guess that's as good as I can do because there aren't any more perfect squares in there. Say you wanted more accuracy, which you get by more rectangles. What are some perfect squares in here? Think outside the box. Give me a value in there that's a perfect square.
0.36.
What?
0.36.
Wow, you think in decimals. That's crazy. Yeah, 0.36 is, yeah, 0.36. I would think of fractions, like,
Oh.
16 ninths. That's a good square root. 9/4. That's 2 in here. That's a good square root.
I think it's.
There's lots of combinations of perfect squares just in there, not to mention 49/16. That's in there. There's tons of combinations of perfect square fraction in there. That's how they got their accuracy. That said, we'll just go with that. Now let's move on to a table kind of problem. Estimate, I got double, this is a double example. Example. Estimate the area under the curve 0 to 8 using left, right, and midpoint rectangles. Are these shucks?
Yes.
Pooh.
Yes.
Are these equal subdivisions?
Yeah.
Yeah, I don't really like this one. That's not really intentional. Never mind. Forget that. Yeah. Darn it. You really need a table problem in there too, but that's not more of an AP style, would be an unequal subdivisions. We'll do that later. All right. You'll get plenty of practice, don't you worry. Moving on to then. All right. Here's where it starts to get a little more abstract. So far it's very concrete. Now it's getting a little more abstract. You are to express an area under a curve starting at a left endpoint 0 using right-hand rectangles of equal subdivisions for any number of subdivisions in an expanded or summation notation. Whoosh.
Okay.
That sounds smart. Let's see if you're smart enough to do what I just asked you to do. Gosh, let's start here. We were saying that when you use equal subdivisions, it's this, yeah? How many rectangles here? No.
Curve. And
N. Height 2 through height N. All right. Let's go a little bit further. The base comes from some change in x. How do you determine the width of each rectangle? 8 minus 0 divided by n. The total width is 8, and you're going to divide it into n chunks. True. Where do the heights come from? F at, yeah, f at some first x plus f at some second x plus f at some third x through f at some last x, yes? All right. The first x, what is it? Okay, I started at 0. When I went to my first base, I went a delta x over. 1 delta x over is 8 over n, yeah? So the first x I put into the function is 8 over n. The next place I do a rectangle is 1, 2 delta x's. That is
16 over n.
16 over n. I'm going to start to try and find a pattern to this, so I'm going to call it 2 8 over n's. The next x at which I find a height would be the third 8 over dot 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 until the last. How many 8 over n's will there be? N. So what is the nth 8 over n? 8. Does that make sense that if I'm using right-hand rectangles, my last value would be at 8? Yeah. Okay. Well then, if I were so inclined, I could do a little bit more and call it something like 8 over n squared plus 1 plus 2. 2 8 over n's squared plus 1 plus dot 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 n 8 over n's squareds plus 1. You follow? Yeah. Okay. Now I would typically refer to this, and most people would, as standard notation. It's expanded notation. However, we will often write this in summation notation. You need to be fluent with both. In summation notation, please understand the two main components. You're finding the sum of many rectangles. The base is always delta x. It could be delta y, but we'll go with delta x. And the height is always some function at different x's. And that x is counting up in a systematic way. That I then is the counting. Now because I have summation notation, I would then say what's the starting I. If you're using right-hand rectangles, then I starts at 1. Because in the first rectangle, you go 1 over to the right side and then find your first height. In left-hand rectangles, you actually start at the left edge, so 0. No delta x is over. All right? What is the last? What's the last I value?
8.
What? N. It's N. How many rectangles do we get? We have 1, 2, 3, dot, 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 N. That counts from the first rectangle to the last rectangle, whatever that might be, and that's the nth rectangle. So from 1 to N. You track it? All right. In this problem, we could go a little more detail specific. We could say that for this problem, delta x was 8 divided by n. And x sub I, if you were to go more specific, it was really just be the x that went in was 1 8 over n, 2 8 over n's, 3 8 over n's, n over 8 over n's. I said that wrong. So what's the pattern to the x's?
X. 8 over
Not x. 8 over n. How many times? Well, that's the counter. 1, 2, 3, 4. So what's the counter? I. I is the counter variable, and the n is how many rectangles. That's okay. How many rectangles? All right. Starting, like I said, to get a little more abstract. You need to be able to work with both. As a Calc 1 teacher, I'd say I'd emphasize both, but as a Calc 2 teacher, summation notation is huge, and so I want to make sure you are fluent. Okay. If you were then to try one on your own, please, try to give me an expanded notation and a summation notation for that bad boy. Actually, I guess I never went function specific. I could have gone one more. Would you also write down the last possible step? The most you could take this to is to say, if the function is x squared plus 1, then that would be 8 over n squared plus 1. Okay? All right. Try it. on your own, and I'll be happy to walk around and help you and enjoy your confusion. Yes? So N is reserved for how many rectangles? So in terms of a counter of what rectangle we're on, we need something that goes up from first rectangle, second rectangle, third rectangle. This really then, this needs to be something different that's counting up. That's why the counter I is attached to that part, not the N. N will be, for any one problem, N is going to be set in stone. It'll be just use 8 rectangles and so, or 7 rectangles. It doesn't count. The number of the rectangle you're on, that's what counts. So that's, I is the what rectangle you're on. So this here would be F at the first X. This would be F at the second X. This would be F at the third X. So I need something to count what rectangle am I on. This, that's I. That can't be N because N is how many rectangles. It's not like N's going to change from 1 to 2 to 3. Once you say, hey, I'm using 4 rectangles, it's 4 rectangles. It can't be the first rectangle set. It's a bit of a mess. Is that about what you have?
Why X over here?
Because I'm dumb. I went crazy. It's 2 over it. Thank you. Okay. Are we good? So far, so almost? All right. Now, that said, these are the easy ones. First of all, we're using right-hand rectangles, which makes things easier. I said, up here we said left hand would start at 0. What would it end at?
N minus 1.
I Excellent. N minus 1 starts and ends at N minus 1. Okay. The next wrinkle besides left hand is if you don't start at 0. A little more complicated then. Actually, never mind. Sorry. This is looking at that a little different way. I'm giving you the area summation, and I would like you to extract for me what is the function and what is the interval. I think I intended the first one to do together. What's the function?
2 minus x.
2 minus x cubed, yes? Okay, and what's the interval? 0 to 3. Excellent. Do the next one. What's the next function? 2x cubed plus x, and the interval? 5. Excellent. All right. Now, if I were to ask you for the interval from 2 to 8 using three right-hand rectangles, with me? What's the first f at? F at what? 4. What's the delta x? 2. Okay. Now then, you can see that that x of I, or the x, the first x that goes in, is no longer simply just a reflection of the delta. It's not f at 2. There's actually 2 components to that x. What are they? What are the 2 things that went into making that 4? Now maybe I'm not answering. Do we all agree that if I use right-hand rectangles that this is my first x, yes?
Yes.
Okay, why did I go here? All right, 2 plus delta x. It's not just simply a fact that delta x is 2, because that would mean I have a 2 here. It's no longer starting from 0. Now the x is going to be a reflection of where did you start and how far did you travel, right?
Right.
All right. So now, if you don't start at 0, things will get a little more hairy. Like, for example, if you're at a left endpoint other than 0, maybe 1, well, then things will be different. The base, what's the base? 7 divided by n. And you're still going to find x at, or f at different f's, or f at different x's, excuse me. Where it starts to be different is what goes into that x, that first x. If I'm using right hand still, what's the first x that goes in?
1.
1 plus
7 divided by x.
7 divided by n. 1 plus a single delta x over. The first one started at 1. I went 1 delta x over and found the height there, yeah? The next height would be, the second x would be to start at 1 and go 2 delta x over. The third height, obviously, would be to start at 1 and go 3 until you ended at the last, which would be f of 1 plus n, 3n. How does that simplify? 8. Isn't that where we end?
Yep.
Yes. Okay. So, at that point then, if I put in the function, it would start to look something like maybe 1 plus 7 over n squared plus 1. And 1 plus 2 7 over n's squared plus 1. Through 1 plus n 7 over n's squared plus 1. Yeah? Would you also write the summation notation next to each of these steps? That first one is like saying a sum of many bases times heights. Notice the base can be brought up front because it's constant. A height differs, so it's in the summation. Or, that's a BH, by the way. The base is always the delta x. I should put delta x here. And the height is still f at sum x. Sweet? Starting at, because we're using right hand, we'll go with the first gap over through the last gap over. More specific then, what is delta in this case? 7 divided by n. And now, the harder part. The x sub I comes from, those are the x's. What's the pattern to those x's?
1 plus 7.
1 plus 7 over n, some number of times I. Yeah? And then if you chose to get more formula or function specific, you could also maybe see the actual function, 1 plus 7 over n I squared plus 1. You see? Good. Try one on your own. Yeah. For now, I'll say if you can go straight to the last step in either, I'm fine with that. Oh, that one is kind of nice, huh? Are you getting something like that? A little more time, or are you good? Move on. I heard a lot of mumble, mumble, mumble. So I'll assume by your mumbling that you're good. Move on?
Yeah.
Right on. Okay. Would you please tell me, for that first one, what is the function and what is the interval? No, actually,
Cute.
yeah, you could actually give two different answers for this. So let's talk about one that you see. What's one that you see? Okay. So one is that it's just x cubed from 2 to 5. Okay, that seems natural. Anybody see another one possibly? What? Who said that? Yeah. What about this? 2 plus x cubed from
0.
0 to 3. Are those the same though? I mean,
Yep.
feels like they're pretty different. This would be this here, yeah? And this would be shifted up to, and from 0 to 3. Same?
Yep. Same
Yeah,
thing.
yeah, they're same. Yeah.
When I put a second equation, when you have to cube like the whole,
Oh, yes, yes. Absolutely, yes. Thank you, you're right. Yeah, left to. So how did my picture still work out? Still have to think about that. Okay, try this one please on your own.
We show all answers. Or
Just give me one answer that you find. On a multiple choice, they would only have one that works, not two, so you just have to find the one that's logical. What's one possibility? F is natural log of x, and the interval is 4 to 9. The width is 5 for sure. The gap here must be 5. You might also say 4 log of 4 plus x, in which case it would be from
0 to 5.
0 to 5. Now what would be problem with that? 0 to 5. 0 what?
0 to
Yeah, the log doesn't really go to 0. Now that said, calculus does handle that question. It's pretty sweet. That's called an improper integral, where you have an integral with an asymptote behavior in there. It's awesome. That's part of calculus too. We will deal with improper integrals. All right, moving along. I'm going to now attempt to teach what normally would take 3 days in 4 minutes. Here we go. Let's do it. So if you were to write this without summation notation, why you would do that, I'll tell you in a second. But let's start here, writing it with summation notation and then dump the summation notation. Notice I'm strictly talking summation notation here, not expanding. Summation notation is to say you add the rectangles. That is always done by virtue of a delta x and f at some x values, and we talked about the components to that x are the starting and then how many deltas over, right? In this case, we're starting at 0, so the only issue will be delta. Let's go a little more specific. What is the delta in this case? 4 over n. The total region is 4, and we're dividing it into some n chunks. F then will be always at some number of 4 over n's, and that counter is our I. And if, again, we're using right-hand rectangles, we're going to go from the first gap over, from one gap over to n gaps over. Now, for this function then, let's start with this. The 4 over n is not part of the counter. It's really out front. And so you can't pull it out front of the summation notation. It doesn't have an I component in it. We do that a little in limit problems sometimes. Now, function. I'm getting ahead of myself. That's not infinite. Sorry. The function in this case is x cubed plus 2x. That means then that I'm going to put 4ni cubed plus 2 4 over n i's each time. Like that. Okay then. Now, our goal is to get a formula that we could use for any number of rectangles. Now, what does this add to? Well, obviously it would depend on how many rectangles, and so that's an issue, but there is indeed a formula for, if I just said the sum of 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, there's a formula for that to n cubed or whatever, call it 11 cubed. There are formulas for that. Now, they're up here. I will always give you them. You do not have to memorize them. But in terms of using them, goes a little like this. First, let's say I cube that. I can cube each part, wouldn't you say? So this is 64 over n cubed, I cubed. Wow. Okay, so I didn't really get to the homework, so I guess you don't have homework. Just, no, or nothing in, just show up on Tuesday.
Wait, what about, you gave us 6
Oh,
back?
6, I think I already put in 6 and 7. Oh, and you
Yeah, but
chose
you
6 and 7 to study from?
Yeah.
Yeah, you gave us back 6. No, no.
We have something without a grade on 6 and 7, we turn it in. I do not need 8, 8 and 9. Now I just can just bring it back. What? I do not want to, we have not finished going over it. Okay, so don't turn in. I thought we turned in 7. Did we not turn in 7?
Yeah.